Hello, in this section of the nuclear chemistry unit, we're going to be looking at the rate of nuclear decay. We're going to learn how to do some calculations with that rate as well as read graphs. And then we're going to finish with the distinction between two different types of nuclear events that you're familiar with. Okay, so as it turns out, each isotope of each element has its own unique rate of decay. Some decay at an extremely slow rate, billions of years, and others are in fractions of seconds, incredibly fast, and everything in between. So what's happening is as alpha or beta particles are emitted from the nucleus, the atoms left behind become different elements. Sometimes the notion of nuclear decay can give the impression that this substance is decaying or disappearing, when in actuality it's just becoming a different element. The same amount of matter is there, a small amount is lost in that these tiny particles are given off, but the sample is becoming a different substance. We call those substances, the original material is the parent element, and the new material is called the daughter element. Okay, the rate of decay is measured in units called half-lives. You've probably heard of a half-life. So a half-life is the amount of time it takes for half of the parent element to decay into the daughter element. Okay, so we can imagine this with a simple illustration of, so if you can imagine you have 40 pennies, and we'll say that the heads-up version of this penny is called the isotope hedzium, and if you shake those 40 pennies, then some of those hedziums will decay into tailsiums. In other words, they'll start heads up and they'll decay tails up. So if you start with 40 and shake them once, one half-life, then statistically half of them would decay into tailsium. If you take those tailsium and set them to the side and then shake the hedziums, then of the 20 hedziums remaining, 10 would decay into tailsiums. A silly illustration, but it's effective. Now, I have a cloud chamber demo from YouTube, but it's not interfacing with this recording device, so I'm going to put those links on the website so you can view them independently. And that's what this is also. Okay, so here we have a nuclear event. It says counts per minute, so there's some kind of Geiger counter or some detection device that is clicking or notifying us of a nuclear event, and there's 80 counts per minute. And then over time, you can see that the number of counts per minute diminishes. Okay, so if we ask, how long is one half-life for this isotope? And we look to go from 80 counts per minute down to 40 counts per minute, how long does it take? And then we trace it down and we can say it takes 2 days. So the half-life for this isotope is 2 days. How many items are left after 2 half-lives? So after one half-life, we go from 80 counts per minute down to 40. After 2 half-lives, first half-life is 2 days, second half-life is 4 days. Trace it up, and we get 20. So half of 80 is 40, half of 40 is 20. What percentage remain after 4 half-lives? So after one half-life, we go from 80 to 40, that's 50%. 2 half-lives, 40 to 20, is 25%. Another half-life, 20 to 10, would be 12.5%. And another half-life down to 5, 6.25%. Or we can just say 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5. 5 out of 80 is 6.25 or 6.5. No, 6.25%. Okay, here's another representation of another type of graph for nuclear decay, and this is for the decay of carbon-14. So if we start with 100%, the relative amount of carbon-14 in this sample, And then after one half-life, which is 5,770 years, you can see that half of the carbon-14 has decayed. Now this gives the impression, as I said before, that somehow matter is being lost, but in actuality, the remaining 50% would be some other element. So I might ask you, if carbon-14 undergoes beta decay, what would it decay into? Or what would the daughter product be? So we have 50% remaining after one half-life, and the remaining 50%, the other 50% would be nitrogen-14. After two half-lives, or 11,540 years, there's 25% carbon-14 remaining, and the other 75% is turned into nitrogen-14. So you may have heard of carbon dating of fossils, and they have to be relatively young fossils, and this is how they tell the age of the fossil, is they compare the relative abundance of carbon-14 to nitrogen-14 in the sample. Here's another form of half-life calculation. I might give you the isotope and tell you that what it undergoes and tell you the half-life. I'll give you the size of the sample and ask you how much will remain after a certain amount of time. Okay, so I'm going to let you stop and think about how you would solve this problem. I'll pause it. So, what do you have to do first? Well, you have to ask yourself, 27 minutes represents how many half-lives? Because after each half-life, half of the parent material will decay into daughter material. So, how many half-lives? Well, 27 minutes divided by 4.5 minutes per half-life would be 6 half-lives. So if we start with a 4-gram sample, how much will decay in 6 half-lives? So the longhand way of doing this is to simply take 4 grams and multiply it by 1/2 6 times. And we would get a small fraction of the original thallium. Another question I might ask you is, what would the daughter material be? And so you'd have to think beta decay, look up thallium, and what do you do with beta decay? Change the atomic number and go up by 1. So look up your periodic table and find what element has an atomic number 1 greater than that of thallium. Now, another way of doing this is with the algebraic equation for half-life. So to find the final amount, which is what we have over here, you take the initial amount, which is what we have here, and multiply it by 1/2 to the power of the number of half-lives. So you take the overall time and divide it by the amount of time for each half-life. Now, some people get thrown by this. If you're not best friends with mathematics, then you might choose to do it the longhand way, or you can do it the shorthand way. Either way, that's how you do half-life problems. Okay, now these nuclear events I spoke of a second ago. You've heard of both of them. So I'm just going to give you a little mental trick and help you to distinguish between them. So the first nuclear event, you have a big, clunky, unstable nucleus. You bombard it with neutrons, making it more unstable. And it becomes so unstable that it actually splits into 2 unstable nuclei, plus more neutrons. This event is called fission. Fission is the splitting of unstable nuclei, large, clunky, unstable nuclei, into smaller nuclei. Okay, now, I might ask you, if I give you all of this, I might ask you to figure out what this element is, and you should be able to do it. So if we start with uranium-238, and one of the products of the fission event is barium-142, what would the other product be? 92 minus 56 is, and that would tell you what this element is. I'm going to make you look it up. If you can't figure it out, ask me in class. And then what would these be? Well, these are additional neutrons. And these neutrons would then bombard this fissionable uranium into more of this, causing the chain reaction that occurs. Where do these chain reactions occur? Well, they're not naturally occurring events. They only occur inside of fission reactors. So nuclear power plants use this kind of activity to produce huge, let me get that slide back up, huge amounts of energy, which is then used to heat water, which is then used to drive turbines, which is then used to create electricity. Okay. Fission reactions also occur inside atomic bombs. All right, the next nuclear event. Small, tiny little atoms fused together into larger atoms, plus huge amounts of energy. This type of nuclear event is called fusion, the fusing of small nuclei into larger nuclei. And fusion is quite common in the universe. It occurs in our friend the sun, and it occurs in stars all around the universe. So it's the most common event, chemical event, nuclear event in the universe. So why don't we use fusion instead of fission? Well, the amount of energy yielded by these fusion events is so large, we're talking the surface of the sun type hot, that normal conventional materials can't contain it. So we have to learn how to either do fusion reactions at much cooler temperatures or learn how to contain them